that fine? Can you hear me? Okay. Good. Okay, so much for that. Now, what I would like to teach you now is to throw an educated look at assembly code as the compiler spits it out and understand what's going on, so you can identify potential problems. And this is not as hard as it looks, because, of course, assembly code is complicated. There are thousands of possible instructions, but you only need probably 20 of them in scientific simulation code. So the number of instructions you need to understand is really, really small. So I hope you bear with me here. Why should we check assembly code? Because the compiler diagnostics is sometimes a little bit scarce. So for example, up to recently, if you asked the Intel compiler to emit vectorization messages, so to tell you whether some loop was vectorized or not, it just said loop was vectorized. That's all very fine, so you can be glad. I think that compiler engineers got paid by this, so the more messages it spit out for standard benchmarks, the better. But the problem is, if it says loop was vectorized, it doesn't tell you how efficiently this was done. So for example, what could happen is that the actual arithmetic, add, multiply, divide, and so on, is vectorized, so it uses vectorized arithmetic instructions, but it does not use vectorized loads and stores. Or it uses vectorized loads and stores, but only half wide. What happens also many times in AVX codes is that you get fully vectorized multiply and add, but only half wide, so SSE wide loads and stores. There's reasons for that why the compiler thinks this is good. I will not elaborate on this, but this is an indication that the compiler didn't really understand what's going on. And this is why we sometimes have to look into assembly code to identify problems. Usually this happens when the performance model that we make doesn't fit to the data that we measure. So we learn something. How do you get the assembly code? It's very simple, and it's also true for the GNU compiler. Not only for Intel, you just add the switch minus big S. So use your normal compiler options that you use to compile your code, and minus big S then gives you the assembly code. If you add the minus O, then in this case it doesn't generate a binary, which is executable. It generates assembly code in this output file. So you can just say less or cat a.out and you see the assembly. If you don't have the source code, that happens from time to time, you can run object dump minus d, a.out. Minus d means disassemble. And then you also get the assembly code. It's a disassembly listing, so you don't have any labels. It's a little bit harder then to figure out which kind of source code or which part of the source code this particular piece of assembly code corresponds to. But sometimes this is also worthwhile if you don't have the source code. Now you might, if you really want to dive into this, you might go into the Intel software development manual 2E and 2A and 2B, or AMD. There's a similar 5-volume set. This is really, really big, okay? So you don't want this. Nobody wants this. So that's why we have these slides. You have to know a little bit about the x86-64 instruction set architecture, which means not only which instructions do we have, but also which registers does the architecture use. How many of them are there and how are they named? In x86-64, we have 16 general purpose registers for integer operands. They are 64-bit wide, and they are called RAX, RBX, RCX, up to RBP. The first 8 were actually present already on the 8086 processor in 1978. So this is a legacy from a very long time ago. They're still named that way. They were called AX, BX, CX that time because they were only 60 bits. Nowadays they are 64 bits. That's why they're called RAX and so on. But there's still the name remaining. And then with the 64-bit extensions came another set of 8, R8 to R15. Okay? The names come from specific purposes for these registers. For example, SI and DI were source index and destination index. RBP is a base pointer. SP is a stack pointer, and so on. AX was an accumulator. So these were special purpose registers. Nowadays, you can do almost anything with every one of these registers. So it's more orthogonal. These are 64-bit registers. They can also be used as 32-bit registers if you substitute the R with an E. then it's 32 bits. Or if you write AX, then it's just 16 bits. For floating point, we have 15 SSE registers. They're called XMM0 to XMM15. They are 16 bytes wide. For AVX, they are called YMM0 to YMM15, and they are 32 bytes wide. And they're also aliased. So there's only one set of registers. So the lower 16 bytes of YMM0 is XMM0. Okay, so much for the registers. These are the registers you will see used in assembly language. Just remember that everything that starts with X and Y is floating point. If you happen to look at assembly code for Xeon Phi, these registers are called ZMM0 to 31. And now the instructions. There are a couple of rules that the instructions adhere to. And for floating point code, it's mostly about multiply, add, load, and store. So we have a so-called AVX or VEX prefix. If the instruction starts with V, it's an AVX instruction. So it's been introduced with the Sandy Bridge processor. Everything without a V was present before. We have the operation that we actually want to do, multiply, add, move. There's also divide, of course, and a whole bag of integer instructions that we're not too interested in. There's a modifier that's sometimes at the end, sometimes in the middle of the instruction. NT is quite interesting, non-temporal. So if you have a huge assembly code, you just grab for NT. I think there's no other assembly instruction that's relevant that uses these two letters in this order. So you find non-temporal stores immediately if you grab for NT. Unaligned and aligned. So if the instruction assumes that the address that you store a load from is aligned to a 16 or 32 byte boundary, it's an aligned load store, otherwise it's unaligned. High is used if, for example, with a load, we only load the high part of a register. So you can load, for example, the upper 8 bytes of an SSE register with a single instruction, and then this is designated by the H and a corresponding L prefix. The width is important because it tells you whether the instruction is vectorized or not. If it's scalar, it carries an S. If it's packed, it carries a P. So packed is good. Okay, packed means semi-vectorized. S means not vectorized. And the data type, single or double precision for floating point. Okay, so this is on one slide what you have to know about how instructions and registers look like for the x86 instruction set architecture. So here's our nice example for array summation. Sum plus equals data of j. So we sum the elements of an array. And we assume the compiler generates the most basic code. No optimizations, just doing what's in the high-level code. So we have a register, which is used for summing up the elements. We have a load for each element. We have an add or accumulate into the register, and that's it. And some loop mechanics. So this is what you get if you let the compiler generate assembly code. Here is the corresponding instruction, bytecode, but that's, I mean, you don't want to look at that. Sometimes you have to, but that's not really, that's an exception. So here we have the address. This is actually an output from object dump. Object dump minus D gives you an output like this. So what does it do? It uses an add instruction, and SS, these two S's have different meanings. The first S says scalar, so this is scalar code, not vectorized. If it were semi-vectorized, I would see P here. It would be at PS. So it's at SS. And the second S stands for single precision. If I had a double precision code, so double here, it would say add SD for scalar double. What does it do? It adds two registers, and it happens that this is an SSE instruction. SSE only takes two operands. So if I want to add two operands, I get a result, and the result always overrides one of the operands. So here I add XMM0 and this, whatever that is, I come to that, and the result goes into XMM0. It's always destination, comma, source. This is Intel assembly syntax. Okay, what's the source? The second source, this is this. And always, whenever you see these square brackets, it's a memory address. It's actually reminiscent of pointer arithmetic in C, in the C language. RDX is the base address of our array. So RDX contains the address of data of 0. It addresses the first element of the array. Our AX is the index, it's J. So J goes into our AX. And since we're dealing with 4-byte floating point values, in order to get the address of a certain element, I have to multiply rex by 4 and add to RDX. It's exactly what happens with C pointer arithmetic. If you add an integer to a pointer, it's implied that you multiply the integer by size of base data type. And that's what happens here. It's exactly the same as in C. Okay, we did the accumulate. Now we have to advance the loop index at rex 1. And we compare whether the loop index has reached the end. Okay? The loop index is an integer. It's using, for some reason here, the full 64-bit register, but for comparing to the final index, it uses only 32 bits. That's fine. Okay? Why it uses rex and not EAX, I don't know here. It's a compiler decision. And then jump above, that's the conditional loop, and it jumps here and does it all over again until this condition is not fulfilled anymore. So that's very basic assembly code for this summation loop. And you agree probably that this is easy to understand. There's a little bit of a complication, because if you generate assembly code on Linux systems, you don't get this nice Intel syntax, which is easy to read. You get AT&T assembly syntax. And I will never understand why the Intel compiler generates AT&T syntax and not Intel syntax for assembly code. If you run it on Windows, it generates Intel syntax. If you run it on Linux, it generates AT&T syntax. Some weird programmer hoax, whatever. In AT&T syntax, it's reverse order, so it's always source, comma, destination. A little bit confusing. And also the address syntax is different. So this is RDX plus RAX times 4 plus 0. So there could be a constant offset added to this address. And the syntax here is much less readable, but it's what you get in Linux by default. Okay, so this is for the simple summation loop. And now let's see what happens if the compiler actually does something to the loop. So this is again our standard code. Then we do the unrolling. We showed you yesterday with the Rufner introduction what the compiler has to do to make this dependence on the register go away, because this code suffers severely from the dependence on the target register. Well, we add to XOM0, and the next add cannot start before the previous add has completed. Each add takes 3 cycles. So in this case, we're getting 1 add every 3 cycles. At 3 gigahertz, this code will run at 1 gigaflop exactly. How do we remedy this? We have to unroll it and accumulate into several independent registers. And that's what we do here. This is 4-way unrolling. Of course, since we have a 3-stage pipeline for add, 3-way unrolling will be sufficient. Yeah? But if we do 4-way unrolling, the compiler always chooses a power of 2 for some reason. Okay, so that's 4-way. We accumulate into 4 registers, XOM0 to XOM3. And then here you see the additional offset that can be put into the address. So this is base plus index times data size plus offset. So we're accumulating 4 successive elements of the array into 4 different registers. And since these are mutually independent, they can fill all the pipeline bubbles. And this code is perfect. It gives you 1 add per cycle, 3 gigaflop at 3 gigahertz. And then, of course, we have to advance the loop counter by 4. And of course, there's a remainder loop, which we now ignore again. Okay, so this is the perfect scalar version of the loop. And now we vectorize it. And you know how that works since yesterday. So in this case, it's AVX, SIMD vectorization. So we have 32-byte wide registers, which can take 8 operands at the same time. So each of those VADDPS instructions is actually a vectorized add that does 8 adds at the same time. 1 instruction. What we do is add the array element to YMN0. And since now we're not doing a single scalar, but a packed add, P, we have to get to the next chunk of 8 elements by adding 32. 8 times 4 is 32. Again 32, again 32. So For each of these loop iterations in this assembly code, the loop counter advances by 32. We have overall a 32-way unrolling. 8-way because of SIMD, and 4-way because of the pipeline optimization. 32-way unrolling. You see it here in the increment for the loop counter. And you might imagine, if this is 32-way unrolled, and your loop count is not a multiple of 32, the remainder loop can have up to 31 elements. And you see this in performance measurements. If you benchmark this loop, and you tune the problem size from 1 to hundreds in steps of 1, you see very distinctive sawtooth patterns. And for example, if the loop length is 63, the first 32 iterations will be in one iteration, and the second chunk of 31 iterations will be in a remainder loop, which is probably not vectorized at all, and even scalar. They are very slow. So if your loop length is a multiple of the unrolling size minus 1 or 2, you have bad performance. And you see these sawtooth patterns if you scan the problem size. And of course, the longer the loop, the less important these remainder effects will be. Okay. Actually, this is not quite correct. The AVX instructions take 3 arguments. So what actually happens is ym0, ym0, address. But for brevity, I've just omitted that. Okay. Now that we see what the compiler does and what vectorized assembly code looks like, we can see how can we leverage that? How can we make sure code is vectorized? Of course, in the best case, the compiler does it all for you. It tells you loop was vectorized. Probably you check using the assembly code listing that everything went fine, and you're done. Okay? Of course, the compiler has to make some assumptions. So for example, you might tell the compiler you're not using any aliasing, the no alias switch over the restrict keyword. There might be some alignment restrictions. For example, some architectures can generate much more efficient SIMD code if arrays are aligned to 16 or 32 or 64 byte boundaries. The Xeon Phi is such an example. On Xeon Phi, you want every single load to be aligned on a 64 byte address boundary. If you can't make sure this is the case, the compiler will generate much more inefficient code because it will do 2 loads for every 64 bytes. So this is really bad. The next level would be compiler directive. So you still have high-level code, Fortran or C, and you augment it with some Pragmas, which seem to be commons for any compiler that doesn't recognize them, but which could be decisive if you want to tell the compiler, okay, in this loop I have no dependencies, because otherwise it can't prove that there are no dependencies. Or in this loop, please vectorize even if you think it's not safe. We'll come to an example later. There are some alternative programming models that you use. So you go away from your standard C and C++ and Fortran, and you could use, for example, OpenCL. OpenCL has some data types that support explicitly SIMD programming. Or ISPC, which is a language introduced by Intel. You could download it for free from the whatif.intel.com website. And it's a C variant which allows you to easily write down vectorized code. So it has some additions for vectorizing loops. But it's still, these are still high-level languages. It's still C-like. Okay? It's not really low-level. The next step that you wish to take, if this doesn't work for you, you can't use it, is intrinsics. Intrinsics are restricted to C and C++. They're like macros that map one-to-one to assembly instructions. So for example, there's an intrinsic for adding 2 32-byte AVX registers using an AVX add instruction. And the compiler will translate these intrinsics to assembly code. The question is, why should I not write assembly code then right away? Because the good thing about intrinsics is you can still use normal variable names. So the compiler takes care of the variable and the register allocation, which is really hard to do if you do it by hand. Now imagine a big code, you have 200 flops, 500 variables. How should you allocate the registers to the variables to make sure that nothing is slower than necessary? Okay? The compiler is quite good at that usually, and the intrinsics give you a way to leave the burden of register allocation to the compiler while still taking control of the assembly language. We have an example later. And you could implement directly in assembler. There are some cases, we will not, but we had one case recently where it was not possible by any of these methods to get decent code. So we had to use assembly language. But that shouldn't really be the standard case. If you want to use intrinsics, you have to include a header file for certain intrinsic, for certain SSE variants or AVX. You can also just include this one. It includes all instruction set extensions. These intrinsics work for Intel compiler at least and for the GNU compiler. Not sure about PGI, and they do not work for Cray, as far as I know. So there's the standard Cray compiler does not support these intrinsics. So here's an example for intrinsic code. Again, this is our array summation using C intrinsics, single precision. You see here we have variables, some 0, 1, 2, 3, and they're not of type float. They're of type underscore underscore M128. This is a variable that has a width of 16 bytes. Okay? It's not a standard C data type. It's specifically for intrinsics. And we have 4 temporary variables of the same type. Okay? And float, scalar, sum, this is our final result. So we initialize the 4 sums to 0, not just assigning 0 to it, but saying sum 0 equals mm set 0 ps. These are already intrinsics, and these map to assembly language instructions that set this register to 0. This is the loop. We have overall 16-way unrolling. We have 4 ways because of SIMD. We have SSE SIMD in single position. That's 4-way SIMD, plus 4-way SIMD because of the pipelining optimization. So 16-way overall here. And you see here, for example, an underlined load is load UPS. This is the address. So you can use your normal variable names, T0, T3, sum 0, sum 3. You can use your normal array addresses, no problem here. So the compiler takes care of all this. But you have control over the assembly language generation. And of course, at the end of the loop, since we've done 16-way unrolling, we have 16 partial sums that now have to be added up. It's your responsibility here. The compiler doesn't help you there. So this is the standard code to add these. I will not go into details here. Okay, you can copy this from the Intel documentation. And at the end, we store the final result, sum 0, into the scalar sum variable. That's it. The assembly code that's generated from this example is this. And you couldn't write it down more efficiently if you did it by hand. Okay? So this is AT&T syntax. So this is source destination. This is a load, another load, another load, another load. We have the accumulate here, the add. We have the add for the loop index, and for the, why is it doing that? It's using a separate loop counter. It's using a loop counter in EAX, and a loop index in RSI. You see the simple address generation here. So the decisions which addressing mode to use is still up to the compiler. You can't influence that, okay? But this is still good code. What you also see is it adds these integers to the loop counters, and the check, the compare, is here. So that gives the integer pipelines a little bit of time to actually do the add, although the add is really fast. It's one cycle. And then we have the floating point adds here, and we jump to the beginning. Okay, this is the loop body. This is perfect. Okay. With the Intel compiler, if you enable an optimization level like 03, it will try to use SIMD automatically. You don't have to do anything special. It just does it. It might not optimize perfectly for the architecture you're running on, but it uses at least SSE vectorization. If you switch on Vec report 3 in this case, it tells you for each loop in the code whether it was vectorized or not. If it was not vectorized, why it thought it was not vectorizable. So that's quite interesting. If you think a loop should be vectorized, then it probably isn't, or it's too slow. Switch on Vec report 3 and you get the reason. The compiler is not very chatty about that. Okay? In the latest compiler, I think in version 15, they put in some more exhaustive vectorization report. But up to compiler version 13, I think 14 also, it's very scarce. You can use source code directives to help the compiler see the loop in the correct light, so to speak. And I will come to that. But first, the command line options. So for example, if you're on a processor which can use SSE2, you can just compile with -X SSE2, and it will run on all Intel machines starting from Pentium 4. Okay? With XAVX, it will run on all machines starting with Sandy Bridge, because Sandy Bridge was the first processor which introduced AVX. And if you use Xhost, that's what we usually use, it will compile for the architecture you're compiling on. So if you're on the front end of a cluster, you know all nodes are the same architecture, including the front ends. You just compile with -Xhost, and you get the optimal vectorization for this architecture, hopefully. On AMD, might be a problem, because if you tell the Intel compiler use AVX and you run the binary in AMD, it will crash. It will tell you that this binary was not compiled for AMD, because there's a CPU check built in, which fails if it sees I'm running on AMD. So on AMD, you have to cut down to -03, which will not give you perfect code on a modern AMD processor. Yeah? Guess why? Okay. Non-temporal stores. Why are non-temporal stores here in this place? They're in this place because non-temporal stores are part of the SIMD instruction set. There's no scalar non-temporal store. So when you want to use non-temporal stores, your loop must be vectorized. That's a prerequisite. On Intel processors, there's no scalar variant. On AMD processors, they have a scalar non-temporal store. That's one of the good things about AMD, but not on Intel. So with Intel compiler, you can influence the generation of non-temporal stores on a global level using the compiler switch upstreaming stores. If you say always, the compiler is allowed to use non-temporal stores whenever it thinks it's safe. Auto leaves it up to the compiler and never switches off non-temporal stores unless you force the compiler, or you tell the compiler using a directive that it should use non-temporal stores in the specific loop. Okay, here to sum up, there are some rules for vectorizable loop kernels. This is taken one-to-one from the Intel documentation. So the loop must be countable, which means, on the other hand, do loops and in C and also while loops cannot be vectorized. The compiler must be able to figure out the loop count, or must be able to generate code that figures out the loop count at runtime, so while loops cannot be vectorized. The loop must have a single entry and a single exit. So things like if condition, exit, or break doesn't work. Straight line code, again, if conditions, rule it out. Whereas sometimes the compiler can do ingenious things in exceptional cases, but in general, straight line code will do, nothing else. And there must be no function calls. Some intrinsic math functions can be vectorized because there's something that's called the Intel Short Vector Math Library, SVML. So if you enable vectorization, you have, for example, an exponential in your loop, the Intel compiler calls a short vector math library, and it will do a vectorized exponential, which is still slow, but at least it's vectorized. Yeah?
If you do a standard call, will that also go into vectorization?
No. A standard call will go to libm, or the GNU library, and this is a scalar, slow implementation. We've done some tests, so if you do a vectorized exponential with the Intel compiler on modern Intel compiler, it will take about 12 cycles per exponential. If you call the C library instead, it will take something between 50 and 80 cycles per exponential. Or what's the different question?
I'll come back to that.
Okay. So these are the prerequisites. You can get better performance if you adhere to the following rules. Use simple inner loops with unit stride. The compiler will sometimes even vectorize loops which do not have unit stride. What the compiler does in these cases is it uses scalar loads to assemble vector registers and then use a vectorized arithmetic instruction. That's complete nonsense. Yeah? But the compiler can then say, I have vectorized the loop. Why is it nonsense? Because as you have learned, many loops are not dominated or bottlenecked by arithmetic. They are bottlenecked by loads and stores. If the loads and stores are scalar, this is the bottleneck. There's no way, no use in doing the arithmetic in a vectorized way. Minimize indirect addressing. Yeah, for example, in a sparse matrix vector multiplication routine, the compiler may vectorize even that loop, but it still has to assemble the register for the right-hand side using scalar loads. So that should be minimized if possible. Data structures should be aligned, especially on architectures which require strong alignment. Xeon Phi is the prominent example. Xeon Phi is really something where you have to take care of alignment. For Sandy Bridge or even Westmere processors, not that important anymore to use proper alignment. And of course, the pointer aliasing issue is a showstopper. What are obstacles? Non-contiguous memory access, and of course, data dependencies. That's the main showstopper. Data dependencies usually prevent from vectorization, meaning the compiler assumes there are dependencies. Probably there are none, and then you can tell it there are none. But if it assumes there are dependencies, it will not vectorize. When the compiler is too cautious to refrain from vectorization because it thinks there's a dependency, you can help it a little bit. There are vectorization pragmas like vector, pragma vector always, for example, but that's only a hint. But there's one pragma that forces the compiler to vectorize. And this is potentially dangerous. If you force the compiler to vectorize a loop, although the compiler thinks it's not possible, you might end up with wrong results. Okay, so this is potentially dangerous. You always have to check. This is called Pragmas SIMD. And Pragmas SIMD is available since the compiler version 12 with Intel. It's nowadays also part of the OpenMP standard, which is strange, the way it is. Here's how you use it. So you use Pragmas SIMD in front of the loop to force the compiler to use SIMD vectorization. There are also some clauses that you can use, very similar to OpenMP. For example, reduction plus X, to tell the compiler I have a SIMD parallel loop with a reduction. I think the point was that such loops are easily vectorized by the Intel compiler, even without the Pragmas SIMD. The compiler knows what to do. But other compilers don't. Other compilers might be okay with very simple data parallel loops, but cannot do vectorization for reductions like this. And this Pragmas SIMD helps the compiler figure out what's going on. And this is why they put it into the OpenMP standard. That's my interpretation of the thing. So always take care. Pragmas SIMD is potentially dangerous. If there's a dependency in the control flow or in the data flow, and you still use Pragmas SIMD, you might get wrong results. Alignment issues, I've told you when alignment might be important. So with modern processors, starting with Nehalem and Westmere, alignment became less and less important on standard x86 hardware. Okay, there's hardly any penalty for unaligned access today. There's one exception, Xeon Phi. On Xeon Phi, if you need to load 64 bytes, because that's the SIMD width of a Xeon Phi processor, and you don't do it on an aligned address, you don't do it on an address which is the multiple of 64, the processor must execute two load instructions, one for the lower part and one for the higher part of the register. So that immediately cuts down your performance in level 1 cache by a factor of 2. And this is why alignment is so important on Xeon Phi. How do you make sure to have aligned arrays? There's a standard POSIX conforming call, POSIX memline. You supply it with a pointer to a pointer and with an alignment constraint. So for example, if you want to have 64-byte alignment, then you put 64 here. So it will align on a 64-byte address boundary, and this is the size in bytes that you get. So otherwise, it works like malloc. You can also free the space using normal free call. Okay, so much for SIMD vectorization. So keep in mind that there are some restrictions when you can use SIMD and when not, and that it's really important, if performance of a loop is important to you, to check what the compiler did. When the compiler said, I have vectorized the loop, it's possible that it's not the best possible code. And throwing a glance at the assembly code may get you more information. Okay. Now, as promised, the next topic in efficient use of parallel resources is CCNuma. And Gerrit's already hinted that the code we've shown before, the stencil code, had a Numa problem, meaning that if you have a Numa system and you run a multi-threaded code on it, you might end up in a situation that all the memory you've allocated is in one Numa domain, sits in the memory that's attached to one socket, but you want to use both sockets. So if you run a multi-threaded code that uses this memory, it's all in one socket, so you have a performance penalty. And this is what this chapter is all about. So again, what is CCNuma? CCNuma means that the whole memory is transparently accessible by all processes, so it's still a shared memory system. Every core in the system can access all the memory, but the memory is physically distributed. So some memory is attached to one processor, while another memory is attached to another processor, but still transparent from the user perspective. If you access this memory, the performance by which you can access it depends on the position of this memory. So it has varying bandwidth and latency. If the memory is far away, it takes longer. So we have a heterogeneous memory access characteristic. And we have potential contention, and I will explain what that means in a minute. So here we have a simple Numa system. We have so-called CCNuma domains. One domain consists of one or more cores or CPUs, and they are attached to some local memory. Here we have two of those domains. So we have two memory chunks here. And between the two domains, there's a more or less fast inter-domain network. So for example, on Intel, this is called quick path. On AMD, this is called hypertransport. So when you run a program on such a system, you may get this situation. You're running your thread or your process here on this core, but you access the memory on the distant domain. And usually, the access characteristics is such that the internode network is much slower than the local memory interface. So if this happens, you have a penalty in terms of latency and bandwidth. This is what we call the non-locality problem. If you have non-local access, performance of the access goes down by some amount. But there's a second problem. Even if you could make sure that this internode network is really, really fast, infinitely fast, and there are nodes, there are architectures in which this network is really, really fast, you still have a problem, because if you run a second thread on the other domain, accessing its local memory, then these two threads will fight for the memory access on the second domain, while the memory interface on the first domain will be almost idle. So there's an uneven utilization of resources here. And this means we have contention on the second domain. That's the second problem of CCNuma beyond locality. It's the contention problem. Now this is the worst possible case. What you should aim for is this situation where every core accesses only memory, almost only memory, that's local to its domain. And you only have to access the neighboring domain for like boundary accesses, boundary exchange, things like that. This is good. The whole question is, how do we make sure we have the right situation, not the left one? We show you how it is decided where the memory goes. That's very simple. You have to remember at first that this placement of the memory is always done on a page-by-page basis. One memory page, one operating system page is usually 4 kilobytes. It could also be more, up to megabytes, depends on the system. But the Linux standard page size is 4 kilobytes. So if you have a page of 4 kilobytes that's aligned to a 4K boundary, it's either in one domain or the other. A page cannot cross the domain boundary. Placement is always done on a page-by-page basis. Okay. Now, first of all, I will show you what the penalty is for non-local access. So this is the non-locality problem. And you can do this yourselves on any Numa system with a simple benchmark that we have in the slides also. So what we do is we have this 4 Numa domain system here, 2 sockets with 2 chips each. This is actually a Cray XE6 node, so 4 Numa domains. And we run a bandwidth benchmark, like the stream benchmark or the vector tribe with a large data set, on one chip. And we place the memory on purpose on another chip. And this way we have 16 combinations, 4 ways to place the program and 4 ways to place the data. So we have a color map that tells us if the CPU node 2 runs the code and the memory is placed on node 0, we have this performance. And it's color coded. Okay? So of course the diagonal here shows us local access. So when the CPU node and the memory node are the same, we have purely local access. We have, in this particular case, a bandwidth of about 13 gigabytes per second. That's what you get on the system. If you have non-local access, for example, memory node 0 to CPU node 1, we go immediately down to about 8 gigabytes per second. And in the worst case, for example, memory node 2, CPU node 0, we go down to about 5 to 6. So there's already a factor of 2 to 3 here in penalty for non-local access, depending where exactly your program runs and where your memory is. So this you should keep in mind. As a general rule, the more Numa domains you have in your system, the more penalty you have to pay for some of these access paths. So for example, if you have 8 Numa domains, you can easily get a factor of 4 or 5 for penalty for remote access. Often, directly neighboring accesses are less expensive than distant accesses, but that's not necessarily so. Okay? So it depends on the hardware. How have I done this? How have we generated this map? Because you know how to pin, how to place threads. Yep. This does not reflect the actual topology of this node. So it's just a color coding of which paths you could take. And I'm not sure what the actual topology was. So this is probably half hypertransport link, and this is a full hypertransport link. So if you rotate the upper socket by 180 degrees, you get probably the right picture. Okay, so how do I want to make sure that the threads and the memory is where I want them to be for this particular benchmark? Of course, you know how to pin threads. You use liquid pin or any other facility that the compiler or the environment gives you. On Cray, you would use AP run. For the memory, you can use Numa control, for example. Numa control not only works as a substitute for task set, it also can influence the way memory pages are placed. So for example, you could just say Numa control minus membind equals and then a list of nodes. So this binary that you start as a wrapper, with the wrapper, will then allocate all its pages on the Numa nodes you specified here. So that way you can restrict the allocation to one or a couple of Numa nodes. Membind means you restrict it. Preferred means you restrict it if there's space available. If there's no space on this Numa domain, the system is allowed to use space from other Numa domains. And interleaved means every new page that this program allocates should go to the next Numa domain, so that all the pages are interleaved across the whole system. And that way you get a sort of parallel access on average. If you don't know how to do it on your own with your code, you can at least run it with interleave and see if something improves, if you have some parallel access on average. We'll have that data for this later. So this Numa map scan can be done with this very simple shell loop. You have two variables, m and c. M goes from 0 to 3, c goes from 0 to 3. You're running a stream benchmark with 8 threads, and you say Numa control dash membind for m, dash CPU node bind for c stream. You could just as well use Numa control and then call liquid pin and then call the binary. Be the same effect. And here's how you call Numa control with interleave. That would make sure that the stream benchmark here would interleave its memory pages across the complete system. So you have some parallel access on average, statistical, so to speak. You will still have contention, you will still have non-local access, but it will be at least parallel and not sequential. Okay, before we go to lunch, I should tell you what the default is without Numa control. So what does the system do if you don't tell it to place the pages in Numa domain 0? And this is what we call the golden rule of CCNuma. The golden rule says a memory page gets mapped into the local memory of the processor or core that first touches it. So if you allocate memory, you initialize it with some data, zeros or whatever. The first time you access a page, writing to it, not reading, writing to it, it is decided upon where the page goes. It goes into the local memory of the processor which initializes the page first. So here's an example. We have this huge chunk of memory, n times size of double. We allocate it using malloc. After the malloc call returns, the variable huge already contains an address. So we have the address. We can store things there, but there's still no mapping at this place between the logical address that we have in the huge variable and the physical memory we have in our system. So the page tables that map between the physical and the logical addresses have not been set up yet. This is being done only when you initialize the pages. So sometime here, someplace in your code, you have this loop, initializing all the data to 0. That's what everybody does, hopefully, in their programs. And this is done by a single thread, which means at this place, in this loop, all those pages will be mapped. And you see this, if you allocate a huge chunk of memory, 50 gigabytes, on your system, and you initialize it, it's very, very slow. If you observe it using top, you see the virtual memory is 50 gigabytes, and the resident memory goes up very slowly, because every time you hit a new page, there's a page fault, you go into the kernel does the mapping between the physical page, the actual DIM, whatever, and the logical page, and then you get it back. You can write to it. That's why it's so slow to initialize memory. Each time you hit a new page, you go to the kernel. So the mapping takes place here, and if this mapping is being done in a serial loop by a single thread, this thread gets all the data in its local memory. And that's the whole problem. Okay? Which means, in order to make good Numa placement, and to make sure that all the data comes parallel from the memory, we have to make sure that these kinds of loops are parallelized. And they should be parallelized in the same way as the loops in which we actually do our work later on. And that's what I will show you after lunch. Okay, see you in an hour.
Question.
Yep.
In C++, you would already, just by doing a do, have made the allocation as a
Yes. Yes. I will say something.